Welcome back to ECE 320A. We're in Unit 4, and now we've learned a little bit about the definition of the Laplace transform. We've applied it to some basic waveforms, essentially the unit step and a delayed unit step. We've looked at finding what the Laplace transform of an operation of differentiation looks like, and that's now multiplication by S in the frequency domain. Let's see how we can apply that information or that knowledge to Laplace transform a differential equation. And just to make this more concrete, let's look at a particular example. Let's look at a second order differential equation, which means that it's a step above just looking at a single derivative. But we now have the second derivative of x plus 3 times the first derivative of x plus 2 times x equal to some arbitrary waveform of time v of t. To introduce notation or terminology, if you haven't yet heard it this way, this equation is a linear time invariant. These coefficients are not functions of time. The 2 and the 3 are not moving around with time. They're not functions of time, so it's time invariant. There's a 1 in front of the x double prime, and there's a 1 in front of v of t. Those are all constants, and this is a differential equation, so it's a linear time invariant differential equation. We have no product terms. We don't have an x times a v. We don't have an x times an x prime. We don't have a sine of x. So this is a linear time invariant differential equation. We want to know what happens when we take this time domain differential equation and run over to the other side of the classroom and put it into the frequency domain. What kind of an expression in this complex frequency variable S will we end up with? Let's now start that or work through that. And if that's the case, we can say, oh, we're simply Laplace transforming the left-hand side, and that must equal the Laplace transform of the right-hand side. Or we're now Laplace transforming the second derivative of x plus 3 times the first derivative plus 2 times x, and that needs to equal the Laplace transform of the right-hand side, which is the Laplace transform of v of t. And we've just learned that the Laplace transform enjoys linearity properties, which says that we can Laplace transform all three of these individual terms on the left-hand side separately. So that we can now say we want the Laplace transform of the second derivative of x. We can pull the 3 outside because of the homogeneity property. 3 times the Laplace transform of the first derivative of x plus 2 times the Laplace transform of x, and that's equal to the Laplace transform of v of t. V of t was just an arbitrary waveform in time, and so we'll just say that has a arbitrary Laplace transform, capital V of s. And now what we want to do is start Laplace transforming these individual pieces, and maybe we'll have to do it in multiple steps because we don't know right now what the Laplace transform of a second derivative looks like. But we do know what the Laplace transform of a first derivative looks like, so let's just apply that one time, and maybe we'll figure out what to do once we see where we're at. Or the Laplace transform of x double prime, let's just now say, oh, we can say that's S times the Laplace transform of the waveform that's one less differentiation than what we started with, so that's x prime of t, minus what? Well, the waveform that's inside this existing Laplace transform, which is x prime, evaluated at t equals 0 minus. This now is all coming from that. Then we have plus 3 times the Laplace transform of x prime, but that's just applying the formula that we just derived. That's S times the Laplace transform of x of t, which is capital X of s, minus x at time 0 minus, plus 2 times capital X of s, that's scaling the Laplace transform of x of t by a factor of 2, is equal to capital V of s. And now what we want to do is simply apply the Laplace transform of a derivative one more time, and then we will not have any more derivatives and we won't have any more Laplace transforms. We'll have everything in the frequency domain and we'll be at the correct location in the classroom. Or we now take s times the Laplace transform of the derivative, which is s capital X of s minus x of 0 minus x prime of 0 minus. That's all coming to us from the second derivative term of x. Then we have plus 3s times capital X of s minus 3 times x of 0 minus plus 2 times x of s is equal to v of s. And now let's just collect terms. Meaning, in some of these, we just have capital X of s, and we have that scaled in various ways. One of the ways it's scaled is with an s squared. Another way that it's scaled is with 3s. And another way that it's scaled is with 2. We now have taken care of all of the terms that are associated with the Laplace transform of the original waveform x of t. Now we need to take care of all of the terms that involve x at 0 minus, and I see that we have this scaling that, and it has a minus sign, and we have another x of 0 minus there, and it has a minus sign also, so we have s plus 3 all with a minus sign times x of 0 minus. And finally we have this piece right there, minus x prime of 0 minus equaling v of s. Or if we want, and we will learn this in a future lecture or video, is we want to actually solve this for capital X of s, and then we'll learn strategies for going back to the other side of the classroom and taking that frequency domain expression for capital X of s back into the time domain. But for the time being, what we need to do is simply solve this for capital X of s. And we can do that by dividing through all terms by this factor or polynomial that's scaling capital X of s. Or we can now say that capital X of s, and pushing everything else on the other side, which means that we're adding s plus 3 times x of 0 minus and x prime of 0 minus, and dividing by s squared plus 3s plus 2, or we now have s plus 3 x of 0 minus plus x prime of 0 minus plus v of s over the same polynomial that was scaling capital X of s. And remember what we started with the definition of our Laplace transform. The Laplace transform we were assuming was one-sided. We were only worrying about waveforms that were defined for non-negative values of time, or from t equals 0 minus up to infinity. So the one-sided Laplace transform enjoys the property that the inverse Laplace transform is unique, and that helps us as we're learning this maybe for the first time, is now let's just concentrate on one-sided Laplace transforms, which allows us now to use or to obtain unique inverse Laplace transforms. Or stated another way, therefore, given capital X of S, we can uniquely find the time domain version or the inverse Laplace transform of that capital X of S. And just like we established notation to go from the time domain to the frequency domain, we'll have similar notation to go from the frequency domain back into the time domain, and maybe you can anticipate what that notation will look like. Now we will say, oh, instead of Laplace transform, let's do the inverse Laplace transform, which says that if we're starting with something in the frequency domain, capital X of S, we want to now inverse Laplace transform and end up back in the time domain with little x of t. And if we now apply that to our example, what we will see is we now have x of t, which is the inverse Laplace transform of capital X of S. And capital X of S actually had two terms. So let's just do those two terms separately. We have the inverse Laplace transform of S plus 3 x of 0 minus plus x prime of 0 minus over s squared plus 3s plus 2. That was one of the terms, plus the inverse Laplace transform of 1 over s squared plus 3s plus 2, scaling the original forcing function or right-hand side's Laplace transform capital V of S. And if you're familiar with differential equations, now you can see that we have two different pieces or two different component parts making up our time domain expression, little x of t. We have one part that's due to the forcing function, capital, which has a Laplace transform of capital V of S. This is now the response due to an excitation function, where that excitation function was little v of t. That's this part of the solution for x of t, and the other part is, if you look at the numerator, that's all due to initial conditions on that waveform to begin with, x of t evaluated at 0 minus and its derivative evaluated at 0 minus, or this particular part of the solution is the part or the response due to initial conditions. And we'll get more comfortable with going back into the time domain from the frequency domain in subsequent lectures, but now you can see that even before knowing how to do that, we can identify the two parts of our complete solution, one part due to how it was excited, the waveform, and if we didn't excite it and we just had initial conditions, then we would just have the yellow highlighted piece. If we had zero initial conditions and only an excitation, we would have the blue highlighted piece making up our answer or waveform in the time domain, little x of t. And remember, x of t is the solution to this second order differential equation. And we'll become more and more comfortable with that. But now what we want to talk about is how do we start, or how do we identify or find such differential equations when we start with an electric circuit. So how do we derive differential equations, either higher order or coupled first order, from an electrical circuit?